Okay, so we've basically finished this chapter now. And after looking at the problems that I assigned, actually, we covered most of the material in class. So I just want to discuss a few things and make a few suggestions of things for you to think about and things for you to do. So my suggestion is, why don't you study the following action? So we'll start off an integral d4x. We'll have the usual free terms. So 1/2 d mu phi minus 1/2 m squared phi squared. Now I'm going to add a cubic term. So minus lambda phi cubed and a quartic term, minus g phi to the 4. And I'd like you to try a few things. So first of all, see if you can write down the Feynman rules. You've done this in naught dimensions. Now do it in 3+1 dimensions. And you'll see it's, again, a very straightforward exercise. If you draw some of the Feynman diagrams, you'll now have a quartic vertex with strength G, and you'll have a cubic vertex with strength lambda. So here, for example, is one of the diagrams that you could consider. Okay, so we've got one cubic vertex, one quartic vertex. Let's put here x1, x2, x3. So what correlator would you be studying now? It would be a time-ordered correlator of phi of x1, phi of x2, phi of x3. So you should be able to write down the Feynman rules for that. The quartic vertex is at a point. Let's call that point X. The cubic vertex is at a point. Let's call that point Y. You have to integrate over the position of the cubic vertex, and you need to integrate over the position of the quartic vertex. For the example that we studied at the start of this chapter, we saw that integrating over the position of the quartic vertex enforced the conservation of energy momentum at this vertex. Check if the same thing happens when you integrate over the position of the cubic vertex. Is it enforcing energy momentum conservation at the cubic vertex? You should conclude that it is indeed enforcing energy momentum conservation. And once again, there's one identity you need. And let me just look for it. I think I didn't erase it. There it is. That formula in the black box is just an integral d4x e to the I x dot k is 2 pi to the 4 times a delta function. That's the only thing that you will need to do the integral over the position of any vertex, quartic, cubic, or anything else. The next thing that it would be very nice for you to verify is that we found that the h-bar dependence goes as some constant, so the same for the complete set of diagrams for your particular correlator, plus the number of loops. So the number of loops controlled the relative powers of h-bar. Why don't you check and see if this rule still holds when you have a cubic vertex in your theory? And you should find that it does. So whatever vertices you have in your theory, always counting the number of loops tells you the h-bar dependence. And that means whenever you do an expansion in the number of loops, you are doing something that is physically sensible. Great. That brings us to the end of this chapter. Let's get going with the next chapter.